All right, first speaker in the short talk session is Philipp Frank. Please take it away.
Thanks, Peter. Right. So I want to take my 5 minutes and spend them on a small method that I've been working on a couple of years ago called geometric variational inference. But before we dive into it, let me just give you a sort of teaser as a context. What does the structure of the Milky Way, black hole shadows, radio galaxies, and supernova remnants have in common? Sort of shifting paradigm a little bit from what we've been talking about the past hour. If you want to really get the most detailed answer to that question, to this day, forward modeling the problem and really doing a probabilistic forward model of the problem and describing how the physics that you want to extract relates to the data that you observe, and then solving this in a Bayesian inverse way still gives you the most precise answer to these questions. If you really want to dig out the last sort of bits and pieces of information that you have in the data set. And a subproblem of that, after you've done all this great modeling, after you've sort of given your way of generating structure, have a prior for what you think could be possibly there, and you have observational data, and you know the relation, you've modeled this out. The subproblem that remains to be solved is how to actually find a subset of, in this case, images or videos that are consistent with the data and the prior that you'd used in the beginning. And one way to tackle this, there are many, many different branches, is variational inference. It's an approximate way to basically say the probability distribution of all the plausible solutions that are consistent with our model in the data. We want to approximate this with a simpler distribution, one that we can work with more easily mathematically, and then try to find one that's a close match in the variational sense, meaning that it minimizes the forward Kullback-Leibler divergence, which is a measure for probabilities. And a very powerful, famous way of doing this is to approximate everything with Gaussians, because Gaussians are great, and we love Gaussians. But in order to go beyond Gaussians to do things better, we've been trying to come up with ways to do this and also approximate non-Gaussian unimodal things, especially these types of funnels that you see here. They are funny and annoying, and they appear all over astronomical inverse problems when you deal with multiple components. And the more annoying thing in astronomy, everything is big, everything's large, so you don't want to do this in a few dimensions or with a few parameters, but usually millions to billions of parameters. When you have high-resolution images, every pixel of your image becomes a dimension in that problem. And so the way geometric variational inference, or short GOVI, tackles this is try to understand what's the geometry of the target function, what's the geometry of the procedure that you're targeting, by taking a look at curvature locally and tracking how that curvature changes across the space as you move across the space, and then essentially build a coordinate transformation using that local curvature information. At every point in space, you get a sort of an idea of how curved things are and how that curvature is changed. And if you track that out, that gives you a coordinate system that tracks how this geometry changes as you move along your landscape. And then you can basically take that idea, take the curvature of your system, and then ask the question, if I have a Gaussian in the reference frame of that transformed space, so basically in that coordinate system that tracks that curvature, and then transform it back into the original space, and I do this in an iterative way, what is a good approximation of my posterior? And that's the whole sort of idea behind GOVI, is getting these, getting still Gaussian approximations, but in this transformed space. And the nice thing about it is that it starts to scale well and works well even to high dimensions if we have an idea of how that, if we can access these gradients and curvature information implicitly, and modern day machine learning has been great at giving us gradients and curvatures of virtually everything once we can write down code for it in modern machine learning frameworks. So the whole paradigm is that it's a way to get non-Gaussian posterior approximations that scales linear with problem size. The number of parameters is exactly equal to the number of dimensions of your problem. So it's a really cost-efficient way to do this. The posterior remains an analytic expression that's useful for things if you want to have an approximate evidence, for if you want to do model comparison and stuff like that. It's fully implicit, no large matrices. It's been applied to many, many places in astronomy over the past couple of years. First and foremost in imaging and component separation, now increasingly also for 3D problems regarding the Milky Way and astroparticle physics. And with that, let me leave you with one application of the local Milky Way dust and the obligatory software slide if you want to play with it. Thank you.
In your latent space, going from the Gaussian to the non-Gaussian distribution through this curvature mapping, is it analogous to a normalizing flow in 2 dimensions, going from a Gaussian to a non-Gaussian distribution? And can you view it that way, or is it?
Yes. In spirit, it is analogous to a normalizing flow or general flow models. The difference is in rather than explicitly parameterizing that mapping and then learning it, we have a way of extracting it from the objective function. So by knowing the metric and being able to evaluate it at a point, we can construct the coordinate transformation implicitly without extra parameters. Yeah.
Let's thank Philipp again. Next up is Sonia.
Hello, everyone. My name is Sonia. I'm a master's student in electrical engineering from the Stanford Computational Imaging Lab. So today, I'm going to give you a high-level overview of how we use the diffusion models in solving inverse problems in imaging, and also highlight the recent work that we've been working on. So the basic idea is that many objects in this real world cannot be imaged directly, mainly due to the hardware limits. And so instead, we rely on indirect measurements. So the goal in inverse problem is to compute an image of the ground truth object X from these indirect measurements Y. And to go from X to Y, we apply the forward model A, which could be either linear or nonlinear, depending on your inverse task. And we also incorporate the noise involved during the measurement process. So what makes inverse problems super challenging is that the measurements we collect are corrupted by many factors, such as PSF, thermal noise, motion artifacts, and etc. And also, inverse problems are ill-posed because measurements are degraded and insufficient, which can lead to multiple potential solutions. So how do we go about solving these inverse problems? Well, the core idea boils down to this Bayes rule. So we want to know the prior of the data distribution P of X, which is typically unknown. And so we utilize plug-and-play pre-trained model to estimate this distribution. We say plug-and-play because you can essentially plug in any off-the-shelf denoiser, such as the diffusion model, which in this case, we'll be using that as our principled prior. The likelihood part is known from the forward model process, so that is the physical constraint we incorporate in our model. Given these likelihood and the prior, we solve the inverse problem by sampling from the posterior distribution, known as the posterior sampling, or we can find the maximum point of this posterior distribution, aka the maximum A posteriori problem. So now you may ask, why don't we just directly use the conditional diffusion model to sample from this posterior? Well, this requires paired training data, which means it's task-specific retraining. And therefore, we prefer the plug-and-play approach because it doesn't require any paired data. We train on clean images only, and it's universally applicable. So the same pre-trained model you have, it works across different inverse tasks. And it's also flexible in designing and optimizing our sampling algorithm to better balance the prior and the likelihood parts. So in my opinion, there are two pillars of diffusion-based reconstruction. One side, we have the pre-trained diffusion model. This is essential prerequisite, so you cannot reconstruct without a good pre-trained model. But then it's more or less solved because to improve your pre-trained model, you really need better or bigger training data. On the other side, you have the sampling algorithm, and this is where the real algorithmic innovation happens, both in terms of the image quality and the sampling speed. So therefore, in our research, we put more emphasis on developing these sampling algorithms. So along that line of work is this dual ascent diffusion for inverse problems, and we recently submitted it. It's a joint work with Axel and Gordon. So what we realized is the previous map and posterior sampling methods require computational approximations that compromise both sampling quality and inference speed. And so we introduced a new approach called the D-Diff to solving map problems with diffusion priors using a dual ascent optimization. We compare our method against state-of-the-art methods and test on 8 different linear and nonlinear inverse tasks, including in-painting, Gaussian and nonlinear deblurring, phase retrieval, and etc. It turns out that D-Diff delivers better image quality across multiple metrics. It's also more robust to high measurement noise levels, and it's more faithful to actual measurements. And plus, it's faster in sampling. So if you're interested, please check out this archive paper we have, and we'll also show this QR code on the last slide. Okay, so the key takeaways from this presentation that I hope everyone learns is that generative AI offers a promising future for solving inverse problems, but we must take careful considerations with integrating these physical constraints to ensure realism and avoid hallucinations. And in this presentation, we learned that diffusion models provide versatility as plug-and-play solutions during inference. And I believe it has a very promising future, especially in challenging domains such as strong gravitational lensing and black hole imaging. Yeah, thank you so much for listening, and we're very open to any collaboration opportunities in astrophysics, so please feel free to reach out as well. Thank you.
Yeah, thank you for the really nice talk. What are the strategies you use to evaluate the samples that you're getting out after you've tried to solve the inverse problem?
Yes, so we evaluate our results against many metrics such as PSNR, SSIM, LPIPS, and also we added another metrics, the residual metrics that measures how faithful our reconstruction is to the actual measurements. Mm-hmm. Yeah, thank you.
Okay, let's thank Sonia.
So if you understand that it's better to have a forward model, but sometimes we don't, and we are forced to use a conditional diffusion model. And I wondered if you compared the posteriors that you get if you use on the same problem a conditional diffusion model or a forward model approach. And did you converge to the same posteriors in good training conditions, or?
Yeah, thank you for the question. So we don't personally compare this method against conditional diffusion models. I think in this paper we wanted to emphasize the superior performance of our method against other plug-and-play style approaches. Mm-hmm. Yeah.
Let's thank Sonia again. Next speaker is. Next speaker is Benjamin Remy.
Thank you. Right. So, Hello everyone, my name is Benjamin Remy, a postdoc at Princeton, and I'm going to talk about deblending and how to train a prior over galaxy images directly from the observation of blends. So I don't know. Right. Thank you. So for ground-based surveys such as LSST or HSC, as you can see here, we observe many overlapping sources due to the survey depths and of the large PSF, and recovering individual image and spectrum for each galaxy is a very hard problem. It's actually an ill-posed inverse problem, as we just saw. For instance, and blending affects like around 60% of the HSC galaxies and also a large fraction of the upcoming LSST survey. So if we don't want to discard these galaxies for our cosmological analysis, and also if you want, for instance, let's say to disentangle AGN with their host, as we heard yesterday from Charlotte, we need the deblending methods. And this is the purpose of our Scarlet 2 codes that we developed at Princeton, where we take into account, assuming that the galaxies are detected, source mixing, conversion with the PSF, and additive noise, and also resampling for multi-resolution. So we frame this problem into a Bayesian framework where we target the posterior distribution, which is proportional to the likelihoods, which is given by our forward model, which is Gaussian, assuming Gaussian noise, and prior over galaxy images, which can be analytical, but as Laurence mentioned yesterday, this will lead to poor reconstruction, or we can also learn the prior from simulations. So with this prior and likelihood at hand, we can solve this problem via optimization, basically just running gradient descents, and we get like very good residuals. But this works, but this only targets the maxima posteriori, and we also requires good initialization of the sources for our gradient descent algorithm. As we just heard about, we can also solve this problem via diffusion sampling. So we're just going to skip this, where we need to compute the score of the posterior, which is just the sum of the score of the likelihoods and the score of the prior that we learn from simulations. And so here you can see one illustration of this sampling procedure where we initialize our sources with just random noise, and this sampling procedure is converging towards the sample from the posterior. And you can see here on the right the residuals that are almost perfect, but almost, because here we trained a prior from actually the outputs of the former version of Scarlet, which was assuming physically motivated analytical constraints, but not like a perfect simulator for galaxy images. But now that we are able to sample from the posterior distribution, we can also use the method that Laurence presented yesterday to update our prior directly from the observations. And so this is also a procedure that has been framed as an expectation maximization algorithm by a paper from François last year, where we basically first need to sample galaxy images from the posterior distribution, and then to retrain or to fine-tune this prior model from these posterior samples. And doing this a couple of times, we are improving the prior and converging to the best prior that we can have from this data. And so this is an illustration of this improvement here on space-based data, HST, where you can see that on the initial, that using the initial prior, we do like a kind of poor inference, but already after the first improvement of the prior, we already have improved the inference of our galaxy images. And the more that we go with these rounds of updates of the prior, the better prior we get, and the better reconstruction we also have until reaching like perfect reconstruction in the end. I'm just going to leave my takeaway slides here, and thank you very much.
We have time for 2 questions.
Yeah, this is very interesting. I wonder, how does this iterative approach, how does it compare with Lucy Richardson, which I guess is like the standard in image?
Say again, please.
Like, I guess Lucy Richardson is like the standard in like image deconvolution. It's an EM algorithm, classical. How does this compare with that? Is it the same, like conceptually, or?
I mean, so this is an EM algorithm where the maybe I may just have to re-say what I said, where the like expectation part is being able to resample from the posterior, and the maximization part is just retraining our score model, and this is equivalent to maximize the likelihoods of our prior.
Yeah, we should connect afterwards, I guess.
Sure.
Thanks.
Thank you.
Another question?
Really cool technique. I'm wondering what the computational efficiency of this is when you're processing tons of images.
Right. So like the most expensive part of these methods is that every time we want to do a new round of fine tuning our model, we need to be able to sample from a lot of data from the posteriors. And for this, we need to each time to sample. To run the diffusion model, and this is the most expensive part of the methods, because then the retraining is just the fine tuning of a network, but sampling is the bottleneck, I guess, of these methods.
Okay, let's thank Benjamin again. Next speaker is Rahul Venkatesh. Please. Just stand up at 5.
Hi everyone, I'm Rahul. I'm a fourth-year PhD student here at Stanford. And I'll be telling you about training predictive models of visual data and how we can use them to probe for causal relationships in natural scenes. So this talk will mostly be about foundation models in computer vision and not so much about galaxies. But towards the end, I'll try to make some connection between the two. So over the past few years, there's really been a paradigm shift across various scientific disciplines. Models are now able to uncover hidden relationships from large unstructured data sets. But perhaps no other domain has demonstrated this revolution better than large language models. These models have shown that if you have enough data and a large enough model, optimizing for a simple next word prediction objective can really lead to some rich language understanding, and has led to a parade of applications which all of us have been using, and has also made companies like OpenAI a lot of money as well. So in this talk, my focus is on presenting a method to you that can sort of transplant this next word prediction paradigm that has worked so well in the language domain into vision. So in vision, the natural analog of next word prediction is next frame prediction, with the idea that by learning to predict the next frame, the model sort of understands the physics and the causal relationships in natural scenes. But unlike an LLM, these models are very hard to prompt, because if you just have a next frame predictor, it's really difficult to ask questions about cause and effect to such a model, even if it has learned perfect frame-by-frame dynamics. So for the purposes of this talk, when I say visual causality, I mean asking a question of the particular form to the model. So for example, if you have a query location here, asking a question like, if I apply a motion at this particular point, which other points in the scene will move along with it? And this kind of a co-movement prediction problem is particularly important for robotics applications. And the current understanding in the field is that it's very hard to probe these next frame pixel prediction models to get this kind of understanding out. So our approach is very simple. Instead of predicting the raw pixels, we propose to predict a motion map, or an optical flow field as we call it in computer vision. So given 2 frames of a video, we use an off-the-shelf model to extract optical flow, a dense optical flow map, which essentially tells you for each pixel in frame 0, which location it goes to in frame 1. And then given frame 0 and a sparse optical flow map, we train a 7 billion parameter autoregressive flow completion model, and we supervise it with cross entropy loss on the predicted flow tokens. And we train this on about 5,000 hours of internet videos. So going back to the example of the Tide bottle, so if we want to understand which parts of the scene will move, if this query point there's a motion applied on this query point, we apply what we call a virtual poke, which is essentially an optical flow input to the model. and have the model complete complete the full flow field, which essentially tells you like which other parts of the scene will move as a result of the poke that we applied. And this can allow us to sort of naturally discover a partition or a segment of pixels, which is sort of like a set of pixels which are causally bound to each other in the space of all possible motions. And we find that we obtain more physically grounded object grouping compared to existing supervised models. For example, the segment anything model here for this Tide bottle only segments out the logo. And in this bus example, it only segments out the windshield and not the entire vehicle, which is actually the movable entity in this case. And the reason for this is basically because these supervised models rely on labels, and actually defining labels for arbitrary object classes is extremely hard. And in some sense, our model sidesteps this problem by sort of having the definition of a segment emerge from a foundation model that has learned to capture the physical dynamics of the world. So we find that, as expected, our model performs much better than pixel prediction methods and also self-supervised representation learning methods. And surprisingly, it's also better than some supervised methods as well, like segment anything. And when we first saw this result, we were actually quite surprised because our model is only trained on internet videos, whereas supervised methods rely on a lot of hand-labeled annotations. So the key takeaways are that we built a foundation model for discovering causal relationships in visual data, particularly trying to understand like which parts of the scene move together. And we found that our model obtains a physically grounded object grouping that could potentially have some robotics applications. And finally, we think that our recipe is actually pretty generic and maybe can be used for causal discovery in other domains as well. For example, maybe images from the LSST camera. And I guess the question to answer here is like, what is the analog for optical flow in this particular domain? And I have some thoughts on that, and if people are curious, I'm happy to discuss later as well. So I'd like to thank all my collaborators. So training these foundation models is very hard, and I could not have done it with all of these people, without all of these people. And we also would like to thank the Marlowe team for the resources that they've given for this project. And okay, thank you all for listening.
Thank you very much. That's great. I don't know exactly how to apply to observations, but I clearly see an application in simulations where you have, snapshots of galaxies and you know that how particles move. So I was wondering, is this has been tried in 3D, for example, instead of just images? Is something that can be done?
Yeah, we have explored a little bit of that, not exactly 3D, but I would call it 2.5D, like providing depth maps as input. So it's not the full 3D structure, but a partial version of it. And yeah, actually, that's the exact same thought that I had, that you can use simulation for getting optical flow, because you sort of know exactly where the particles move. Right. But if you just have images from LSST, maybe you cannot actually get optical flow. So I had the same thought, actually. Yeah.
We have time for one more question.
I think we solar physics have a wonderful case for your applying your algorithm. That we have something called surface flux transport, means that the active region that of the sun that we observe in magnetic flux, and it will migrate along with flow, the flow of the plasma that carries it, and it will migrate and dissolve and also grow and decay depending on circumstances. But that thing has a particular importance of application because, say, for example, if the active region, they are observed on the near side, like the Earth side of the sun, and as time goes on, it will rotate to the back side of sun that we can see. And we use that flux transport model to predict kind of what they will be on the backside when we don't see it. And we usually, like just like yours, we approximate the flow of the magnetic flux. But and seems that you can just use yours to do this by your algorithm instead of physically modeling the or approximate its flow of the feature.
Right. Yeah. That sounds very exciting, and I think I agree with your point that you can actually have the physics sort of like learned by the model rather than like baking it into the parameters. I guess it depends like how much data you have to train the model. Like here we needed a lot of tokens to train this model, but if the similar thing exists in that domain, then I think we can explore that as well.
Yeah, we can talk offline.
Sure.
I think, I think I found a wonderful application.
Thank you.
Let's thank Rahul again. And the last speaker in this session is Sebastian Wagner-Carena.
All right, thank you for having me. Excited to tell you guys a bit about some work here that I've done with Aizan and Sydney. Sydney being a student here in the audience, so if you guys want to ask her questions afterwards, she can tell you about it as well. And this is, we're calling it a data-driven prism, multi-view source separation with diffusion model priors. So let's start quickly with a motivating example that sort of brought us to this problem. We would like to know what a galaxy looks like. Generally, when you ask this question to an audience, they give you some description of a galaxy that looks like that very pretty image I'm showing you on the right there. But in reality, when we actually observe galaxies, our images look a bit more like this. And that poses a lot of challenges. Obviously, the data is noisy, but there's also a lot of components to that image which are not what we think of when we're thinking of galaxy light. Random stars or distant galaxies that happen to fall along the line of sight, that if we were to simply define the galaxy light as whatever flux we're seeing in these images, would be an incorrect representation of what a galaxy actually looks like. And another way to describe this is if you take random sight lines that are not targeted on galaxies, which is what I'm showing you on the left, you see that some portion of the signal that I'm seeing on the right could just as well be described by a model that was trying to fit the luminous profiles we have in the left-hand side of the image. So, with this motivating example, the idea would be I would really like to have a prior for galaxies. I'd really also like to be able to take these images of galaxies and tell you what part of the light comes from a galaxy and what part of the light comes from these like random backgrounds and foregrounds. And I would like a model that can do all of this with multi-resolution data that has noise and some missing part of the pixels. And unsurprisingly, the solution to this kind of problem is very similar to what two of the talks already presented today, which is diffusion model priors built through expectation maximization method. So this is an outline of Francois Roset's previous work. The idea here being I have some sort of incomplete observation space, which is the top row right there. Over time, I build a better and better diffusion model prior through like the trivial expectation maximization algorithm, which works by starting from my imperfect prior, taking an expectation step, which gives you those really noisy samples up top, using those imperfect samples to build a slightly better prior for the maximization, and just repeating that until I reach convergence, which is that last row there, which has a really nice understanding of the prior of natural images and can therefore give me very nice posterior samples despite my incomplete observations. So here we want to take this one step further and imagine now that I don't have one observation and one prior. I have multiple types of observations and multiple types of priors. So here's a nice little schematic representation of that. Here I am showing you three types of observations: the blue type of observation, the red type of observation, the green type of observation. They all consist of the same types of underlying sources, but as I go from blue to red to green, a specific type of source is more enhanced in that kind of observation. And that would be, for example, galaxies versus just observations that have all the random line of sight light. And the principle is to say we can use these same kind of diffusion model priors to actually jointly sample from the posterior of all three of these objects. I start with a very poor understanding of what the different priors are for my blue, my red, and my green component, which is what I'm showing you here. And as a consequence of that, I get a really poor separation. So clearly there in the image, the blue, the red, and the green have not been well separated. But I can plug this into the same kind of expectation maximization strategy and learn a better understanding of what the blue signal looks like, the red signal looks like, the green signal looks like, plug that back into the expectation, get a better separation, repeat the maximization until I get a really nice separation of the three types of source signals underlying this one observation, and of course the final diffusion model that I can use for prior sampling. Okay, so I won't walk you through all the examples we have in this nice paper or the math given the limitations of the time, but I'll hopefully show you one example to sort of convince you that this works. So imagine I have a bunch of images of what ImageNet thinks is grass, which is not really grass all the time. I then downsampled it really nicely, so some of those images have really low information content. I also have a lot of images where I have different observations of grass, and someone has thrown some zeros and ones on top of them. And what I would like to learn is that in these observations, there are two fundamental distributions, grass images and MNIST digit images, even though ahead of time I haven't told my model what either of those two things look like. What my goal is to take the images up top, to train this joint sampling of the diffusion models through expectation maximization and end up with things that look like these true grass samples and the true MNIST samples, which are the things that I injected into my image. But I didn't never have access to those labels, as is traditional in this like inverse problem space. And here I'm showing you how the model trains over time. So you can see it goes from really poor understanding of what the grass and digits look like to much stronger understanding. And by the end, on the high resolution images, I have nearly perfect posterior samples that really match the true images. And in the low resolution, I have some convincing set of posterior samples that seem to capture what the grass and digit images could have looked like underlying these observations. And again, this separation is done without any labels, without any understanding a priori of what digits and grass look like. And we have some nice metrics in the paper to sort of argue that statistically these things seem representative of the distributions that we're trying to capture. And then just to finish by circling back to the original motivation, imagine I wanted to do this for galaxies. We can do something very similar where we separate out the galaxy light from the background, foreground light, and we get some very nice convincing separation of these HST images that lets us to build a nice prior on galaxies. And I'll just leave you with these thoughts that we probably want to do these types of source separation problems for future astronomical data, and diffusion models are a very nice strategy for approaching that.
We have time for about 2 questions.
I guess one question would be how, in the example that you gave, you need to know in advance, right, that you're looking for 2 source distributions. I'm sure you've.
Yeah, so the thing you assume, so obviously if you assume you don't know how the sources are mixed and you don't know what the sources look like, you're cooked. It's like a fully degenerate problem. Yeah. So the assumption we want to make here is that you have some understanding of the mixing matrix that moved you from the source space to the observation space, but you have absolutely no idea what the sources themselves look like. And so, in the galaxy example, this would be like I've built some very nice catalog of galaxies, and so I know in some images galaxies are there, and I know in the randoms I should have no correlation with the galaxy sample. And so I'm just trying to learn those 2 source distributions with knowledge, of course, that one set of images has one source distribution and the other one has a different mixture. Yeah.
One more question.
How would this work if, let's say, your zeros and ones were randomly scaled in size? Would it still be able to recover?
Yeah, so I didn't show it here, but you can do something where you have, if you know the scaling and you know some information loss ahead of time for the individual observation, like you know the PSF or you know like a change in resolution that's happening for your observations, it works perfectly because it's like, this same concept that the previous speakers were presenting of like you have a prior, you have an understanding of the transformation that takes you to your observations, and so you can use this one prior for all of your observations. If you didn't know what the transformation was, then the prior you constructed would also have those scalings because it would be seeing those scalings in the data. You wouldn't be telling it that those scalings were a transformation that was imposed from the source to the observation space. And so your final prior would be a bunch of like zeros and ones with different scalings.
All right, let's thank Sebastian again.